So my name is Mike Heap. I'm from University of Strasbourg in France. And as the title suggests, today I'll spend the next 10 to 15 minutes presenting a pilot study on whether we can use whole rock oxygen isotope ratios as a proxy for petrophysical, like rock properties. And so those of you who know me will know that I'm not anything to do with isotopes, or not normally, but I have some friends that are isotope experts, and it's been really superb. What I like to do in research is work on collaborative projects, and this has very much been in that spirit. And so, yeah, be gentle with isotope questions at the end, I think. So I thought that it would be a good idea to present this to the VMSG community, because I know from previous talks and previous conferences that there's a lot of you who are isotopic experts, and so so I thought that I would pick your collective brains about this, and I felt a bit left out. So this is me gegging in on isotope geochemistry. So to provide some motivation, it's conventional wisdom that hydrothermal alteration, which is largely ubiquitous at volcanic sites, it's conventional wisdom that this increases the likelihood of dome or flank collapse by compromising stability. So what we have here is a photograph of La Soufrière de Guadeloupe in the Eastern Caribbean. This is the dome here, and we have a rainfall triggered partial flank collapse here, this little landslide. And what you can see, hopefully, is that there's a lot of whites and yellows from the collapse scar, and this is because the rocks are very hydrothermally altered. So I think there's this conventional wisdom, which is the third time I've said that now, that there's some marriage between alteration and stability of volcanic slopes and domes. And so to get to the point, large-scale models designed to study these processes, which I think are important, rely to some degree on measurements of rock physical and mechanical properties. So some modeling studies here. So this is a paper that I published last year in geology, and then another paper in geology here by Claire Harnett. So these are, hopefully you can tell that these are volcanoes and domes. These are large-scale models designed to look at flank and dome stability hazards. But then it poses a question: if we don't have rocks, or we don't have these petrophysical properties to put into these models, then what do we do? What if sampling is impossible, for example, if it's way too dangerous, or we can't collect blocks that are big enough to perform these laboratory experiments, then what do we do? And so finding independent proxies for these sorts of values becomes quite crucial, and could represent a step change in our understanding or our ability to monitor these sorts of hazards. And so this is where whole rock isotopes can come in. So I've been reliably informed that these whole rock oxygen isotopes can serve as an indicator of alteration, and that these values will increase as a function of relatively low hydrothermal alteration, or low temperature hydrothermal alteration. At high temperature, the values can increase. So we're definitely talking about a certain type of alteration here, which is quite common to volcanic domes and around the world. So the goal here is to test whether we can use these whole rock isotope values to ballpark rock physical properties, which are the petrophysical goodies that go into these large-scale slope stability, dome stability models that I showed in the previous slide. The key thing here, or what's really nice about these measurements, is that it requires a very small amount of material, and I'll explain some of the cool implications, or what I think is cool, later on at the end of the talk. So for this work, we're going to go to the Caribbean. We're going to go to the island of Guadeloupe in the Eastern Caribbean, to La Soufrière de Guadeloupe, which is a hazardous and frequently collapsing andesitic stratovolcano. It is absolutely full of hydrothermal alteration. The alteration is also expanding on an almost daily basis on the top of the dome. This is the top of the dome here. And volcanic unrest has been increasing since the volcano reawakened in the early 90s. So it's definitely a volcano that we should have our eye on, especially with respect to this link between alteration and collapse hazards. So we went to the volcano and we collected samples from different sites around the volcano. So this is the dome here. We collected 19 samples from around the volcano. Most of them are from the dome area. These samples were big blocks, and then I took them back to the lab and I drilled out samples to measure uniaxial compressive strength, Young's modulus, and tensile strength. And these data are published in previous contributions. And so these are those petrophysical goodies that I was talking about that go into these models. So these were measured on these blocks. So we also measured the mineral composition using X-ray powder diffraction of these 19 blocks. And then samples were also sent to Cape Town, to Chris Harris, to measure their whole rock oxygen isotopes. So this is the first graph that I'd like to show you. So we have whole rock oxygen isotope value on the y-axis here, and this is the percentage of weight percent of secondary or alteration minerals. So this is from the XRPD, the X-ray powder diffraction, and this is the isotope value here. So some pictures of some of the samples in the top here to give you an idea of what the rocks look like, and you can see definitely if you compare this one to this one, then you could argue, or it'd be hopefully easy to convince you that this one is more altered than this one here. So each of these points represents one of the 19 blocks for which we have a weight percent of alteration minerals and a oxygen isotope value. And so don't look at the colors. The colors refer to something that I'm not going to talk about in this talk. So just ignore the colors for now. And so hopefully you'll be able to see that oxygen isotope value increases as a function of the weight percent of altered secondary minerals, so how altered the rocks are. So that was the first, quite satisfying result that the oxygen isotopes are tracking the how much alteration there is in the samples. So the first set of mechanical data. So now we can plot the uniaxial compressive strength. This is the laboratory measured strength of the rocks as a function of the oxygen isotope value. So each one of these points represents a cylindrical sample, like you saw in the previous slide, the guys on the top, that's been squashed in the lab until it broke. And this value represents the strength, the pressure, the stress, sorry, at which it broke. So each of the points represents one of these samples. And we assumed that the oxygen isotope value was constant for each of the individual plugs cored from the blocks that we collected, if you're following. So what you can see, hopefully, if you ignore these guys up here, what you can see is that the strength, with the eye of faith, the strength decreases as a function of increasing oxygen isotope value. So that's for uniaxial compressive strength. So here are two other petrophysical parameters that were previously measured on these materials, tensile strength and Young's modulus. And we can plot these petrophysical parameters also as a function of the oxygen isotope value. And hopefully what you can see is a bit more difficult with the tensile strength up here, is that in general, the tensile strength and the Young's modulus are also decreasing as a function of increasing oxygen isotope value. So again, each of these points represents a single experimental sample that was broken in the laboratory. And the reason why they form these little chains is because we have multiple samples cored from the same block, which is given a single oxygen isotope value. So that's why it looks a bit strange. So we're going to have a lot of time for questions. So because we're interested, the whole point of this study was to see whether we could use these values as a proxy. So if you don't have enough rock, or if you can't get the materials, or maybe you don't have all the fancy machines that we have in Strasbourg, whether you can estimate these values which are important for these models using the oxygen isotope values. And so what we did is we made some very, very crude empirical relations between the compressive strength, the tensile strength, and the Young's modulus with the oxygen isotope values. So it's literally just a line, a best fit line drawn through these data, ignoring the naughty one, which was up here. And there is a reason that we can exclude this one. H32 was quite far away from the dome, so I think it has. I'm pretty confident it has a very different alteration history, which is why I hope this is why it plots up here. We also exclude this one. These guys had quite a lot of macro fractures in, and there was some problems with the experiments. So if we ignore these outliers and we throw in similar data for Mount Merapi in Indonesia, which are these green squares here, we can come out with these empirical relations, which if you know your oxygen isotope value, then you can ballpark your strength, your tensile, your compressive strength, tensile strength, or your Young's modulus, with various caveats, obviously. So the conclusions are that I hope that you're slightly convinced, at least, that it was worth having a go, at least, that whole rock isotope, oxygen isotope values could be used to estimate rock properties if you're in a pinch. What's great is that they only require a very small amount of material. And so here's a few of the interesting implications or interesting uses of some sort of techniques like this. Say if you have a borehole in your volcano, or even in your geothermal reservoir, and you only have chips from your borehole, you could use this method to predict parameters that you wouldn't be able to with small chips. So that's quite I think quite a useful take-home point. Also, if sampling large blocks are impracticable, then say it's way too dangerous to collect some larger materials, or you're in a very remote area and you can't bring big blocks back, then this is another method, this method would be useful to ballpark the petrophysical goodies. And this was a suggestion from Jean-Christophe Komorowski, that maybe you have a deposit that is way too friable or broken up to be able to make measurements or collect blocks, but you could use this method to reconstruct the dome strength from the deposits. So obviously care needs to be taken because there's loads of caveats, some of which are listed here. I guess I was blabbing too much. We published the paper last year, so you can check it out if you want. And if anyone's keen, or if you have any ideas of ways that this could be a lot better than it is, then come and see me. And thank you very much.